different bin widths can reveal different patterns, right? So let's make smaller be the diamonds data set where we filter the carat, where we filter for diamonds that have carat values less than 3. So this is like a smaller subset of the diamonds data set. And then let's plot the histogram of the carat column for the smaller data set. Okay. And we'll set the bin width to 0.01. Okay. So this is a distribution for the carat column when we filter for, values less than 3. And so you can see that, compared to this, right, we see different patterns now because now we're zoomed in. Above, we had a more general distribution. It was very fluid, right? It keeps going down and down and down. But in reality, when you zoom in, you can see that there are bumps, right? There are almost 2 peaks instead of 1 that we saw here. So keep that in mind as well. Depending on what you're trying to figure out and that kind of stuff, you might want to zoom in and plot different versions with different bin widths and so on and so forth of your data and of your plots. Now, to overlay multiple histograms, you can use geom poly. I don't know how you would say that, frequency polygram, I guess. And let's go ahead and do that as well. So the smaller data set, let's go ahead and view the histogram of both the carat and the color and the cut. But we're mapping cut to the color aesthetic. And we want a freak poly with a bin width that's 0.1. And there we go. So for the whole range of the carat values that are possible, we've now created essentially 5 different plots within a single plot. And these plots all correspond to a different cut. And so why is this useful? Because here, we found the general trend of carat, right? But what if, based on the cut, there were radically different trends? So imagine, like, in general, all the cuts have the same distribution going down, but for some reason premium, it goes in the opposite direction. But overall, because premium has less diamonds than the other ones, let's say, overall the distribution would be going down. But you would be missing this extra piece of information, right? So it's good to plot them out like this. In this case, right, they all just in general tend to be following the same trend, except I guess that's interesting is the good diamonds, they do seem to go up, in fact. So they do seem to increase in number as the carat value approaches 1, but then they go back down and they drop off pretty quickly. Okay. Now, we can answer questions about outliers, right? So let's plot the smaller data set, where we filtered for less than 3 for carat value. And let's plot carat, right? And we'll plot the histogram of this with bin width far smaller than what we did before, right? Now this reveals an even more interesting pattern because now it's so fine, right? It's so granular. And we can see that, there are interesting phenomena that's going on, right? Where it just shoots up and then drops off gradually. And then we have like this group out here, which is pretty lonely. But in general, they do seem to be categorized by, certain ranges. So, this gives you some idea of where the bulk of the diamonds are located. And this does seem to be like an outlier here, outlier values, like unusual values, which is something you might want to consider. Specifically, let's plot a histogram of the Y column. And here we see that all the values seem to be gathered around here. But let's do something here. Let's limit the y values to between 0 and 50. Okay, because look, this is a very high range. Because there are so many diamonds in this range, it might be covering up the fact that there are some here. Because if there aren't some here, you know, there's really no reason why ggplot2 would extend y all the way up to here. So let's zoom in on, don't get confused by, so this y refers to refers to our y here, okay? But here, when we're setting the y limit, we're referring to the y-axis, which is a count. So because there are so many diamonds in this area, it might be hiding some here. So we want to zoom this axis down into 0 to 50. So let's do that. And there we go, we've zoomed in. In fact, let's actually do this down here so you can see them both. And then we can just delete this. So we've zoomed in. And there we go. Now all of a sudden we notice that there's not only, you know, there are about 8 diamonds that have 0 for some reason. And then we have one way out here and one way out here. So this is a classical example of an outlier. These two, we covered these in the presentation, the introduction to this section. This is something, you know, that's gonna have to be considered, right? So this might pretty dramatically throw off some statistics and some results, but at the same time, you know, you have to come to a conclusion of whether or not these are mistakes or not, right? These could very well be mistakes, and so it would be best to remove these two values, even this one, right? Because how can you have a diamond that has a 0 width, or what was y? Y was, yeah, width. So you can't really have a diamond with 0 width, right? So either these are very small values, and we can actually test for that, right? Let's just go into diamonds, and let's go into y, and let's limit to like 10, 0 to 10. So they are zeros. So that's interesting, right? X's are also zeros, Y's are also zeros. So what's happening here is most probably that these values just weren't filled in. They might either have not been filled in, or they might be so small that it just rounded. So based on those possibilities, you have to decide as a data scientist what to do with these. Do you ignore them completely but potentially lose a lot of valuable information in these other columns? Or do you remove the X, Y, and Z columns for all the rows and just forget about them, ignore them, and just work on these? Or do you find a way to fill in these? So we can do something like k-means clustering, imputation, or we've covered some of this in the pre-processing section, where you can impute values here based on what the average of either the whole column is, or the average of the values that these columns have been filled in when these values are most similar to the ones you see here. So when you cluster all of these together and you have clusters, the ones that are closest to these, what values do they have for X, Y, and Z? So there are different ways of imputation. We covered all this in pre-processing, but that's a decision you have to make. The same thing goes for up here. Let's filter for like 20 to like 30 to 60. There we go. We have these, we found these two, right? So we have this one and this one are these two. So they have huge Y values. And, you know, this kind of makes sense because the caret is so big. You know, it's not that big actually, right? Compared to 5.5. So, you know, these do seem like anomalies, right? They do seem like they're mistakes, or they're just very rare, unusual cases. So depending on your answer, you know, what problem you're trying to solve, you're going to have to make a decision. And when you're preparing your report, you should make sure to mention the assumptions and what you did. So if you do end up removing these two, mention it in your report that those two instances have been removed, and explain the reason why. Maybe calculate how far off they are from the mean and or from the next highest value or something like that, and then put that as a reason for why you eliminated them, because they're very clearly outliers, right? So as long as you always specify your assumptions, it's all right, right? Because even if you arrive at the wrong conclusion, the assumptions are there, and all you have to do is correct your assumption. Something to keep in mind, right? You could just plot this and you can see this and you just move on, right? But then when you zoom in, you notice there are outliers. So always be aware of like the extremes and the ranges and how big of a number 12,000 is, for example, compared to 0 and that kind of stuff. Now so we were able to locate these unusual values like so, but if we want to get them here in our environment and not visually, then we can do so. So let's go ahead and just take diamonds, and we know that y is less than 3, right? We're trying to find these ones here, or y is bigger than 20, so we're trying to find these ones here. And let's select just let's say the price, X, Y, and Z columns, and let's order by Y. So these are all the unusual instances, all the unusual diamonds. And so, it's interesting that, for example, this has 0 width, but it's more expensive than, this one, which has almost 60 millimeter width. So, not millimeter, I think it would be nanometers, or not, yeah, millimeters, right? So yeah, and then at this point, in the worst case, even if you do continue using data as it is, you'd be able to put this into a report showing people that these are the unusual values and so on and so forth. Now let's deal with missing values. Missing values. So we dealt with unusual values. Let's deal with missing values. Let's take diamonds and let's filter for y values that are between 3 and 20. So now what we're essentially doing is we're removing the outliers. We're removing the unusual values. We're just taking the diamonds that are here. So we're assuming that these are unusual and these are not supposed to exist. So we're filtering to remove those. Okay. And let's save this as diamonds 2. And then we can go ahead and plot diamonds 2. And get an idea of the distribution, because keep in mind, this distribution was thrown off, right? And this is a very good example of why it's very important to deal with unusual values or outliers, because look, when you look at this, you see that there's a skew. You see that, there's a skew towards lower values. But if those two values were removed, that would not be the case, right? It would be spread out across here and it would have a completely different distribution. Maybe it's actually skewed towards the left. We don't know. So now we can filter out the outliers, and then we can replot the histogram, and we can set the bin width to 0.5, and okay, we didn't run this. Okay, so this is a very common mistake. ggplot2, uses plus signs, not pipes. Okay, let's go ahead and run that. And now we see a more accurate distribution of the y values. As you can see, they're like almost 2 peaks, and this is the distribution, right? So this is the actual distribution of the y column. But here we don't get to see it because it's thrown off by these outliers. Right, so it was a good decision removing the outliers. Now we see a more accurate distribution. Now we can replace values with missing values, right? So like, for example, let's take diamonds and let's create a new y, or like let's change the existing y, mutate it. If y is less than 3 or y is greater than 2, we put an NA in its place instead of 0. Otherwise, we just keep it as it is. Okay.